Measure of relative standing, Z-scores. In an earlier chapter, we saw how to use percentiles to determine how one result rates based on the dataset it belongs to. This method is suitable for small datasets. Another method for determining relative standing is to use Z-scores or standard scores. The Z-score of a result in a distribution tells the number of standard deviations that the result is away from the mean. Thus, a Z-score of 2 says that the result lies 2 standard deviations above the mean, while a Z-score of -1 says that the result lies 1 standard deviation below the mean. Z-scores work for all distributions, not just those which are normally distributed. So for example, if we have a Z-score of -2, that means the result lies 2 standard deviations below the mean. If we have a Z-score of -1, it means the result lies 1 standard deviation below the mean. If we have a Z-score of 0, then it is the mean. The result is the mean. If we have a Z-score of 1, it lies 1 standard deviation above the mean. If we have a Z-score of 2, it lies 2 standard deviations above the mean. And if we have a Z-score of 3, the result lies 3 standard deviations above the mean, and so on. And obviously if we had a Z-score of -3, it would lie 3 standard deviations below the mean. It's just not in this particular example. The Z-score corresponding to the mean is 0. If this symbol is the standard deviation, then the Z-scores corresponding to the mean plus the standard deviation, the mean plus 2 standard deviations, the mean minus a standard deviation are 1, 2 and -1 respectively. Suppose Mary scores 80% in an English test and the class mean and the standard deviation are 60% and 10% respectively. Then to find her Z-score, we're going to use our standardizing formula from our formula book. So we're going to have 80, which is our x1, minus 60, which is our mean, divided by 10, which is our standard deviation, which gives us 2. Thus, her Z-score is 2, i.e. she achieved 2 standard deviations better or above than the mean. One of the main uses of Z-scores is to compare results from 2 or more completely different sets of data, whether they are normally distributed or not. Peter has 2 tests in 1 week at school, maths and physics. In maths, he scores 84%, while the mean and the standard deviation for the class are 70% and 12% respectively. In physics, he scores 74%, and the mean and the standard deviation of the class are 61% and 6% respectively. By calculating Z-scores, determine in which exam Peter did better relative to his classmates. The key word here is relative, so compared to his classmates. We will call Peter's score X in each case and calculate the corresponding Z-score, and we're going to use our standardizing formula to do that. So for maths, the mean was 70, the standard deviation was 12, and the X value, which is his score, was 84. So we have 84 minus 70 divided by 12 gives us 1.17, corrected 2 decimal places. In physics, the mean was 61, the standard deviation was 6, and the X value, which is the score, was 74. So again, using the standardizing formula, we have 74 minus 61 divided by 6 is 2.17, corrected 2 decimal places. So notice that 2.17 is greater than 1.17, and 2.17 related to physics and 1.17 related to maths. As Peter's Z-score for physics is higher than his Z-score in maths, he performed better in physics relative or compared to his classmates. So although he got a lower grade, he got a grade of 74 in physics compared to 84 in maths, he actually performed better in physics relative or compared to his classmates. If the data is normally distributed, we can use the Z-score to determine the percentile of an individual result. Suppose a large number of students sit an exam and that the marks are normally distributed with a mean of 60 and a standard deviation of 15. If Stephen scores 83 in this exam, in what percentile is he among all the students who sat the exam? Knowing his percentile, gives him an idea of his relative standing to his fellow students. Recall that percentile refers to the percentage of the results that lie below the result in question. Below is the key word here. Because the marks are normally distributed, we can use the standard normal tables to determine Stephen's percentile. If we let the normal variable x stand for the mark obtained to calculate Stephen's percentile, we need to find the probability that x is less than 83 and convert this number to a percentage. So as the mean is 60 and the standard deviation is 15, we're going to use our standardizing formula. So we're going to have 83 minus the mean, which is 60, divided by the standard deviation, which is 15, which gives us 1.54. Thus, the probability that x is less than 83 is equal to the probability that z is less than 1.54. So we go to our tables, and we get the probability that z is less than 1.54 to be 0.9382, which gives us 93.82%. As 93%, not 94%, of the results are below Stephen's, he has scored in the 93rd percentile. The same method can be used to determine what result is required to achieve a given percentile. So the probability that z is less than 1.54, we go to 1.5 and go across, we go to 0.04 and go down, and we get 0.9382, which again gives us 93.82%. In a university exam, the marks are normally distributed with a mean of 65% and a standard deviation of 8%. The university decides to give first-class honours to the top 10% of its students. What is the least percentage required to achieve a first-class honours in the exam? Give your answer correct to one decimal place. To get a first-class honour, a student has to be in the 90th percentile or higher. Because if a first-class honour goes to the top 10%, then you have to be in the 90th percentile or higher, because 100 take away 10 leaves us with 90%. Let x be the normal variable representing students' marks. For x, the mean is 65 and the standard deviation is 8. As 10% is equal to 0.1, we first want to find z1 such that the probability that z is less than or equal to z1 is equal to 1 minus 0.1, which is equal to 0.9. z1 is the value below which 90% of the area under the standard normal curve lies. From the standard normal tables, we get z1 equal to 1.28. This equals 0.8997, which is approximately 90%. I'll show you on the next slide exactly where this number came from. Let x1 be the mark which corresponds with this value of z. Then, using the standard formula, we let it equal to z1, which in this case is 1.28. So we have 1.28 equals x1 minus the mean, which is 65, divided by the standard deviation, which is 8. So 1.28 multiplied by 8 is 10.24. This is equal to z1 minus 65. And 10.24 plus 65 is 75.4. So z1 is equal to 75.4, correct to one decimal place. Thus, a student needs a mark of 75.4% to achieve a first-class honour. So now let's have a look and see where did we get this number from. So z1 is the value below which 90% of the area under the standard normal curve lies. So from the standard normal tables, we got z1 equal to 1.28. So what we have to do is look through all the numbers and see what is the closest to 90%, or 0.9. And we see that 0.8997 is closest to 90%, and this corresponds with 1.2 and 0.08, which gives us 1.28.